In this video, we're going to do some examples evaluating limits with direct substitution. And what does direct substitution mean? Well, if P and Q are polynomials, and to remind you, a polynomial is any function that's made up of powers of a variable. So x squared, y cubed, anything that takes polynomial form. We're not talking specifically about quadratics here. While quadratics are polynomials, not all polynomials are quadratic. So if P and Q are polynomials, and C is a real number, the limit as x approaches C of P of x is going to be exactly P of C. And what do we mean by this? Well, we just mean that if the limit exists, if it's possible that we can just plug in C, then we can just plug in C to figure out what the limit is. And more so, the limit as x approaches C of P of x over Q of x is going to be equal to P of C over Q of C. And so the story by the end of this video is just going to be, if you can plug directly in, then you can plug directly in to figure out what the limit is. And that'll become more obvious as we do a few examples. So let's do a few examples. So let's take the limit as x approaches 2 of 2x squared minus 3x plus 1 over x cubed plus 4. Now, via our limit rules, we have a quotient here, but we know that the limit of the quotient is just the quotient of the limits. So we have the limit as x approaches 2 of 2x squared minus 3x plus 1 over the limit as x approaches 2 of x cubed plus 4. And from here, we can just plug directly in because we see that we won't get a 0 in the denominator. So if I plug 2 directly in, I get 2 times 2 squared minus 3 times 2 plus 1 on the top. And on the bottom, I get 2 cubed plus 4. Well, 2 times 2 squared is 4, so that's 8. Minus 3 times 2 is 6, plus 1, over 8 again, plus 4. Which is 3/12, and I will reduce to 1/4. And so in the end, what we have is the limit as x approaches 2 of this function is equal to 1/4. Similarly, we have the limit as x approaches 6 of 2x minus 1 times the square root of x plus 3. Here I have the product of two things, and the limit as x approaches 6 of this product is just going to be plugging in 6. So we get 2 times 6 minus 1 multiplied by 6 plus 3, which is 12 minus 1 root 9, which is 11 times 3, which is going to give us 33. Now, what if we can't directly substitute? What if I had a function like this? The limit as x approaches 1 of x squared minus 1 over x minus 1. Well, I can do some algebraic manipulations that we all know how to do to try to make it so that I can plug in 1. So I see that this is equal to x plus 1, x minus 1. I factor the top over x minus 1. And from here, I can cross off these x minus 1s. And if I do that, what I'm left with is x plus 1, and the limit as x approaches 1, in fact, this is the limit as x approaches 1 of x plus 1, is exactly 2. And if we graph both of these functions, we would see that our function x squared minus 1 over x minus 1 is identical to the graph of the function x plus 1 at all points besides at the point x equals 1, where there is a removable discontinuity. Similarly, let's do one more example like this, we could say the limit as x approaches 3 of x squared minus 3x over 2x squared minus 5x minus 3. And I can start by trying to plug in directly. And if I try to plug 3 in directly, what I get, I'll choose a different color, what I get is 2 times 3 squared minus 5 times 3 minus 3. 3 squared is 9 times 2 is 18 minus 15 minus 3, and we see immediately that in our denominator we would get 0 if we plugged in 3. So instead we do what we just did, we factor the top. I get x minus 3. I'm going to factor the bottom as well. Factoring the bottom, I'm going to multiply this 2 by this 3, and then remember that I did that. Hold on to that 2. I get x squared minus 5x minus 6. Then I'm going to ask myself, what two numbers multiply together to equal 6 but subtract to equal 5? The answer is 6, negative 6 and 1. So we get x minus... We get x minus 6, x plus 1. And you can multiply that back out to make sure that you did it right. And then we have this 2 up here that we have to not forget about, so I'll bring the 2 back. And on the left side, I'm going to simplify, and that gives me x minus 3, 2x plus 1. So that's the bottom factored. So on the top, I have x times x minus 3. On the bottom, I have x minus 3, 2x plus 1. I can cross off these x minus 3's, and what I'm left with is the limit as x approaches 3 of x over 2x plus 1. And if I plug 3 in, I get 3 over 3 times 2 is 6, plus 1 is 7. We end up with 3/7. Let's keep going with a couple more examples. What if I have something like this? The limit as x approaches negative 1 of root x plus 2 minus 1 all over x plus 1. And a question you should ask yourself here, maybe pause the video and see if you can figure out how to manipulate this function to get the limit. But the thing that should jump out to you is that there's a root here, and whenever we see a root, we very often need to take the conjugate. The conjugate of a root function, if I have the root of something minus 1, is just going to be the root of that thing plus 1. We just switch the sign. And watch what happens when I multiply both top and bottom of this fraction by that. We get root x plus 2 plus 1, root x plus 2 plus 1. Notice we are multiplying a fraction, both top and bottom, by the same thing. That is completely allowed. And if I FOIL the top, I get root x plus 2 times root x plus 2 is just going to be x plus 2 with no root. And then we're going to get plus root x plus 2 with this term, but then we're going to get minus root x plus 2 with this term. The two are going to cancel, and we're left with just the minus 1 times 1, which is going to just be minus 1. And that's across the top. On the bottom, we have x plus 1 times root x plus 2 plus 1. And I'm going to leave it in that format. You might already see why. Because 2 minus 1 is 1, so we get x plus 1 over x plus 1 times root x plus 2 plus 1. Which means we can cancel the x plus 1 over x plus 1, and we're left with the limit as x approaches negative 1 of 1 over root x plus 2 plus 1. And now we can just plug directly in. When I plug in negative 1, I get 1 over root negative 1 plus 2 plus 1. which is 1 over root 1 plus 1, which is 1/2. Awesome. Continuing, we'll do another practice problem. It might help to pause the video as I write the practice problems and see if you can figure out how to solve them before continuing. So if I have the limit, we'll do as x approaches 1 again, of 1 over x plus 1 minus 1/2 over x minus 1. This is also a little bit of an algebra review. Here, once again, we can't just plug 1 in, but you should see that you have fractions and fractions are never fun. So we're going to get rid of the fractions and then see where we're at. If I want to get rid of fractions in a fraction, I take advantage of the only fraction rule we know, which is I can multiply the top and bottom by the same thing. In this case, I'm going to multiply the top and bottom both by the least common multiple, or the common denominator of the denominators. Here we have 2 and x plus 1. So we're going to multiply by 2, x plus 1. And then we have to multiply the bottom by 2, x plus 1 as well. And let's see what happens. When I multiply this first function by 2 times x plus 1, I'll have 2 times x plus 1 over x plus 1, which is just 2. The x plus 1s will cancel. When I multiply by the second function, we will have 2 times x plus 1 over 2. The 2's will cancel this time, and we'll be left with x plus 1. Notice I put the x plus 1 in parentheses because of this negative sign. This negative sign is going to have to distribute there. And that's all over x minus 1 times, put this in parentheses, times 2x plus 1. Now 2 minus x minus 1 is going to be 1, 2 minus 1 is 1, minus x, over x minus 1, should have a parenthesis, 2x plus 1. Okay. Now we multiplied it out. I said things would work, but things don't seem like they worked. We didn't exactly get something that can cancel. But another algebra rule to remember in this case is we can pull a negative sign out of anything we want as long as we flip all the signs. So if I'm looking at the top, I have 1 minus x. That is exactly negative x minus 1 over x minus 1, 2x plus 1. Now we have x minus 1s, which can cancel, and we're left with the limit as x approaches, I think we wanted x approaches 1 in this case, of negative 1 over 2x plus 1. And now we can plug 1 in directly, and we get negative 1 over 2 times 1 plus 1, which is 2 times 2, which is negative 1 over 4. Now, what if we can't use our laws? What if we have a problem like the limit as x approaches 0 of 1 over x plus 5 over x times x minus 5? In this case, we have the limit as x approaches 0, which means we're going to have a 0 in that first denominator, and we're also going to have a 0 in that second denominator. One thing that we could try here is combining the two functions. Here we kind of have the limit as x approaches 0 of an f of x plus a g of x. Let's combine those functions, and the only way we know to do that is by having a common denominator. So let's start there. We see that this has an x in the denominator, this has an x in the denominator, this has an x minus 5, this does not. So we're going to put an x minus 5 there by multiplying top and bottom both by x minus 5. So in our first term, we have x minus 5 over x times x minus 5. Plus, in our second term, we have 5 over x minus 5. Now we see we have the same common denominator, so we can add across. We have x minus 5 plus 5, which is just x over x times x minus 5. We have something that can cancel. We can cross the x's off, and we're left with the limit as x approaches 0 of 1 over x minus 5. We can plug 0 in directly and get 1 over negative 5.